Hi everyone. This is the first time I'm doing a YouTube live, so just bear with me here. I don't know how the settings operate. Let me just go on Twitter and tell people that I'm now live. There were 9 people and now there are only 5. Okay, that's fine. Okay, so let me just quickly go onto Twitter and say that I'm live. Okay, thanks for those of you that are joined in already. And thanks to those of you that tweeted me and DM'd me on Instagram with your requests on what you would like to see or what you'd like us to cover. I'm going to go through as much as I can today. Maybe if a need arises, we can roll over. I'm just going to switch this other light off. Sorry, 1 second. If time does not allow it, we might just roll over the rest of what we were supposed to have done tomorrow. Okay, I'm gonna start with a small element of mukbang because I haven't had supper yet. So I'm gonna eat a little bit while we discuss this. I don't know how this is gonna go. So let's just give people a few minutes just to log in. Okay, I'm really hungry. Okay, so we did say that we're gonna discuss what's gonna be in the test, and the objective is for me not to reteach what we've done, but just to outline specifics of what we've covered, right? Just to outline specifics of what we covered. Some of you asked me to cover the entire chapter 2. That's not possible, right? That's not going to be possible for me to do. We have to deal with specifics here, right? So we cannot deal with, I can't do the entire chapter 2. So I'll have the chat running. I don't know how to view it. How do I view it? Okay, so I think that the live chat is open. So if you want to send me any questions that you want me to answer specifically, we can do that too. Okay, so I'm gonna try and answer as many questions as possible, and my apologies if I don't get to everybody's questions in today's session. But if you don't, if I don't get to it, then you're more than welcome to consult with me tomorrow and Wednesday during lunch, right? So tomorrow during lunch and Wednesday during lunch, I will be available for consult. Okay. I'm having chicken pasta for anyone that's interested. Okay, so let's start with chapter 2. And chapter 2 was on modeling of continuous systems. So some of you are asking, well, what happens then with chapter 1? Obviously, chapter 1 is still at play, at large, and at large, saying that because whatever we do in chapter 2 is based on what we just done in chapter 1, because the solution procedure is one of the steps in the modeling process. So I'm just going to run through the steps with you quickly, because I think that some of you are struggling with given a question, where do we start, right? And the supplementary notes that are a good basis for understanding how to mathematically describe a model. So the first step is to identify what the problem is, okay? And this entails writing out what the given problem is in a very clear way, that allows you to translate what you've written out very easily into some mathematical formulation. Okay, so we whatever the problem is, if it helps us to restate it, then we would restate it. So for example, some of the models in the notes, the way in which the problem was stated, the problem was stated was clear enough that it did not warrant me needing to identify what the problem was. Okay. The second step is to make any assumptions, and this here in both population modeling and radioactive decay was a key step in the modeling process. Okay, a key step in the modeling process is to underline what are the assumptions that we're making. Okay, so for example, when it came to radioactive decay, one of the key assumptions that we made with a radioactive substance was that there was nothing else coming into the substance or nothing else affecting the rate at which the substance was decaying. The rate at which the substance was decaying was only decaying with respect to the mass of the substance itself. So any other factors that possibly might affect the mass of the radioactive substance, we neglected them for the purposes of our model, right? We said that they were negligible, and the only effect was the mass itself decaying with regards to itself. Then with population modeling, we started out by unpacking, Langivia threw in unpacking if he's on the live video. We talked about population modeling, and I unpacked for you all of the factors that may influence population modeling, that may influence a change in the population. And those factors ranged, right? There was a range in those factors. We talked about the birth rate and the death rate, the common ones, and then we went on to more specific factors like use of contraceptives, GDP, geographic location, uh, wars. We spoke about multiple factors, immigration, that may affect the growth or the change, whether the change is growth or decay, not really important at this stage, but we spoke about many factors that might affect the change in the population. But when we considered the models that we considered, we only considered the important factors of birth and death rate. We only considered the birth and death rate as the ultimate factors that were affecting the change in my population. And we derived specific models related to those assumptions that we made. So that's a very important assumption and a key assumption. And I also told you the reason why we make assumptions. The reason why we make assumptions is to make our model simple enough that we can find solutions to it. One of the key things is towing the line between simplification and robustness. So we'd want our model to be as robust as possible, but still simple enough that I can understand key issues that the model is raising. Okay, and the population model, I like the build from model 1 to model 2 to model 3 because we increased in complexity. We started with a very simple model where the growth was just exponential, right? There was nothing else governing the growth except the birth and the death rate. In model 2, we then incorporated an element of a carrying capacity, and we saw how having a carrying capacity now changed the way in which our model behaved, right? Having a carrying capacity, our solution then, or the population would grow until it reached a stable point, and that stable point was governed by the carrying capacity of our population. However, the second model still had deficiencies, and we needed to adjust that model even further to account for problems that we'd encountered with the second model. So that's the key step under assumptions. Yeah, under assumptions, that's the key step. Once we've got our assumptions, the next step is to classify our variables. And this is a very obvious step and doesn't need me to go into too much detail, right? That just deals with given a model, what are the variables that are important, right? What are the variables that are important, and the variables that we need to consider and that we need to define. Once we do that, the next step is to construct the model. And this is where a lot of students, I think, are finding difficulty, is how do we construct the model and how do we know that our model is correct? How do we construct it? And how do we know the model is correct? And that is step 4 and step 5. One key point that I want to mention here is that modeling is a trial and error process, which means that sometimes you're going to come up with a model and that model is actually not the right model, so you've got to go back and adjust. Okay, and the way in which you go back and adjust is governed by step 5, and step 5 is problematizing the model. Problematizing the model means going going to the construction of the model that you found in step 4, looking at it and unpacking whether that model makes sense. What are our expectations for this model? What are our expectations for this model? And does the model that we've come up with meet those expectations? Right? So for example, when you talk about population growth, or yeah, let's look at population growth because it's an example that we covered. If we're on population growth and our model, if our carrying capacity is greater than the current population, we have certain expectations. And if our model doesn't meet that expectations, then we need to go back and refine the model in order to incorporate those expectations. Quickly running through this, the next step is then to solve the model, and this is where chapter 1 comes into play. The element of solving the model comes into play from chapter 1, and that means that chapter 1 is fair play, right? It's examinable, right? Because we've covered it, and it comes into step 6 rather of the modeling process. And then step 7 and step 8 is, once you've solved the model, how do I interpret, verify, validate the model, right? And how do we interpret, validate, and verify? We look at our solution. A good way to verify or validate your model is through looking at what it looks like graphically. And some of you struggling with that a little bit, it seems, the graphical analysis, right? What does the graph look like, and does that graph meet our expectations for the model? Right? Does the behavior exhibited by our solution meet our expectations, right? So we can verify and validate the model in that way. And then we can look at key aspects of the model and see whether it makes sense, right? So for example, under population modeling, we looked at what would happen if the carrying capacity was equal to the current population, and what would happen if the current population was 0. And under those conditions, we looked at whether our model made sense, for those key characteristics. And then the last step, which is step 8, is to refine the model. We refine the model then to incorporate any of the things that went wrong. Any of the things that went wrong, we can refine the model now, and we did that going from model 1 to 2 and model 2 to 3. Right? We refine the model to take into account things that did not work. Okay, so that is the step-by-step process of model building. While I'm here, I'm just going to talk about one of the TUT questions that it seems like some of you are struggling with. And that is question 4 of TUT 2. Not question 4 of TUT 2 was I'll show it to you quickly. Question 4 of TUT 2 said, let n be the size of the population of a certain country, and suppose that the maximum population size that the country can possibly sustain is n, and suppose further that the rate of growth of the population at any current time t is proportional to both the current population size and the difference between the maximum population size and its current size. Okay, so if I stop there, the formulation of that model is clear. The rate of growth of the population is proportional to both the current size and the difference between the maximum population size and its current population size. Okay, so if we quickly try and write out that model. Okay, if we quickly try to write out that model, that would be dn by dt is equal to n into n bar minus n. Okay, that would be how we would formulate that model. Okay, we'd formulate that model as the rate of change of the population is proportional to both the current size of the population and the difference between the maximum population size and the current size that the population can attain. So if I go quickly to model 3 of population, That was precisely the formulation that we had here. That's model 4, sorry, that's model 2. If I go to model 3, right? And so we formulated them in this way. And the question that I asked you at this stage is that which of these two formulations is correct? Is this the correct formulation, or is this the correct formulation? Right? And I hope that you went through the same steps as we did in model 2 to decide between these two. To decide between these two formulations, you've got to see what happens when n bar minus n is greater than 0 and less than 0. Right? And what that means is what happens when our current population is greater, sorry, what happens when the maximum population is greater than the current population, and what happens when the maximum population, or the carrying capacity, that's the term that we call the maximum population, the carrying capacity is less than the current population. And this formulation that we have here is the correct formulation. The one thing that I'm missing here is my proportionality constant. Okay, so once you do this, you can solve this differential equation. You can solve this differential equation. And the solution to that differential equation is given at the bottom here. Okay, that's the solution to that differential equation. N of t is equal to n bar over 1 plus n bar over n naught minus 1 e to the minus n bar kt. Okay, then the next question is, if we look there, the next question, or the next part of the question says, sketch by inspection rather the graph of this function, and that should be easy for you to do. That's just graphing the solution. And then the last question, or the last part, is what I think some of you are struggling with, and that says, when is the rate at which the population is increasing a maximum? When is the rate at which the population is increasing? When is the rate at which the population is increasing a maximum? Okay, and I think that a lot of you are struggling with understanding what that means. Okay, so a lot of you are struggling to understand what that means. I don't know how YouTube works because I can't seem to see the chat. I've seen someone ask something, but I don't know where that's gone to now. Okay, the way in which we answer that question, it said, when is the rate at which the population is increasing a maximum? Okay, so I actually purposely left that out of my slides. Right? I purposely left that out of my slides because one of the questions that we did in class, actually asked us to do that also. Right? One of the questions that we did in class also asked us to do that. So I want you to think about what that means. When is the rate at which the population is increasing a maximum? When is the rate at which the population is increasing a maximum? What that is asking us to do is, it's asking us to find, based on the solution that we found for n, based on the solution that we found for the population, what is the rate of change of that population, right? So this equation here at the bottom, what is its rate of change? Right, so I've got to first differentiate this. I've got to first differentiate this, right? And once I've differentiated it, the question then becomes, at what point is that derivative increasing? Okay. So let me unpack for you what that means. So you're going to find the solution. You're going to find the solution for n. Once you find the solution for n, you're going to differentiate that solution, right? That is the rate of change of the population. Okay, this is the rate of change of the population. Okay, they want to know when this bit here, when the rate of the population is increasing, is a maximum. So to find where the rate of change of the population is a maximum, you need to find its rate of change. You need to find its rate of change, and you need to equate that to zero in order to find where the rate of change of the population increasing is a maximum. Okay, so the point where the population is reaching a maximum, the point where this is reaching a maximum, there you would have to find where the rate of change is equal to zero. To find where the rate of change of the population is a maximum, you need to find where the second derivative is equal to zero. Okay, so that is the distinction that I want you to understand when it comes to that question. When it comes to question 4, that is what they're asking us to do. Okay. Then when it comes to decay models, I think a lot of you are struggling with understanding what how do we work out those compartmental models? How do we work out those compartmental models? And what I said to you very early on in chapter 2 is to think about each problem, each modeling problem, in terms of the water tank analogy. Think about each problem in terms of the water tank analogy. And if you can do that, the question becomes easier to understand and easier to formulate. Okay, so when we had the radioactive substance, or when we had the decay, formulate that in terms of the compartments and see what the flow rates are, right? The substance itself, a radioactive substance, is a substance that's decaying to the environment. Okay, it's a substance that's decaying to the environment by some act of radiation. So we have some substance, there's radiation that's applied to that substance, right? And that substance then reduces in size. Okay, if you think about a tumor, that's what we're doing with a tumor, right? We're applying radiation through chemotherapy, in the hopes that the size of the tumor will reduce in size, will break down in size. Okay, and that radioactive substance, whatever it may be, is being lost. Whatever is being decaying is being lost. Okay, but in our compartment model, right, if you remember the second model for radioactive decay, what we said was that we had a radioactive substance, and that radioactive substance was changing into another non-radioactive substance. Okay, we had one radioactive substance that decays into another non-radioactive substance. Okay, so in that case, whatever is decaying of the first substance is no longer being lost to the environment, it's no longer vanishing, but it's being positioned into another non-radioactive substance, B. Okay, so whatever is decaying from A turns into B. Okay, so that's important for you to understand. Whatever's going out of A, whatever's decaying from A is going into B. And the nature of A being radioactive means that whatever it's decaying, it's going to decay from its original mass until there's nothing left of the mass itself. Whatever its original mass is, and up until such a point that the mass is then zero. But that mass, from the original mass to zero, all of it that's decayed has now gone into another substance B that's non-radioactive. Okay, so if you think about those compartments, there's a element of the decay flowing into another compartment, which is B, and that substance is not decaying because it's non-radioactive. Excuse me. Whatever's coming into B stays in B. Okay, and that was model 2. Model 3 was then we had a non-radioactive substance, A, flowing into another substance that's non-radioactive, and that whatever results from that was flowing into another substance, C, which was non-radioactive. Okay, so in this case here, A was decaying, and it was decaying, and whatever it was decaying was turning into B. Okay, and so B initially is nothing, so it accumulates with whatever decays from A. Okay, and so B starts increasing. B starts increasing with all of what's decayed from A. But B itself is a radioactive substance, so at some point, B itself starts decaying. Okay, so when we'll look at it graphically in a second. B itself starts out growing, and at some point, the amount that's coming into B from A is less than the rate at which B itself is decaying, and so then it starts going down. Okay, because then it gradually starts decaying because the rate of its decay is higher than the rate of inflow of of A. Sorry. Okay, and so B itself is a radioactive substance, and so that substance itself is decaying, and that's decaying into substance C. Okay, and then substance C grows with whatever's coming in from it from B, and then it increases in growth because now there's more that's decaying, into it from B. Okay, then the last one, and the last one, which is model 4, is where I think many students got lost. So in model 4 we had still 3 compartments. We had some radioactive substance A that turned into another radioactive substance B, and that subsequently turned into another non-radioactive substance C. Sorry. The difference here was that A itself, which was radioactive, no longer had an initial mass. No longer had an initial mass. So, as it stands, there's nothing governing the system because A, B, and C, all three have a mass of 0. So, the fact that it's radioactive, A and B are radioactive, means nothing because there's nothing to initiate the system. Okay? There's no mass that's initiating the system. All of the substances have 0 mass. However, the question says A is supplied at a constant rate to the reactor. Okay, so we have some substance A that's non-existent at the moment, but there's something coming into A at a constant rate. There's a mass, a continual mass that's coming into A at a constant rate. Okay, so there's a rate now coming into A, and that rate is now changing the mass of A. As it comes into A, the mass of A is increasing, right? And then everything else stays the same. Okay, it's coming into A, it's decaying into B, and whatever's whatever's in B is then decaying into C. The difference here now is that none of those substances are going to decay. None of those substances are going to decay. And the reason for that is because there's always this constant rate of mass coming into the system. Okay, there's no longer conservation of mass in this question. Okay, remember the other question, so the system was a closed system. The system was a closed system, so there was always conservation of mass. However, with model 4, there's always a constant supply coming into it, and so the conservation of mass is no longer in effect. And none of those substances decay. Okay, if we look at what that looks like graphically, none of those substances decay. Right, so A is in blue, so you can see A starts off growing slowly because of the amount that's coming into it, right? And then it reaches some steady point, right? But it's continuous, it's not going to drop down. B is in orange, so B starts off slowly because there's less of it coming into it. And then as a constant rate comes into it from A, B itself starts increasing until it reaches a steady point. However, everything is decaying into C, and so C will grow exponentially, right? There's nothing leaving it, and there's always a constant amount that's coming into it, and so it will grow exponentially. And that is how we verify our model, right? Our expectations of what we thought would happen is what took place. Okay, so that's how we verify our model. Does anyone have any questions? I don't see someone saying no. Do you mean you don't understand? Please, can you just clarify? I want to switch gears a little bit. We'll come back to the modeling section if anyone wants me to go over anything specific. I cannot do like long questions because it's not easy to facilitate that on YouTube. So a question, uh, it was in the differential equation, do we make the constant rate? Do we make the constant rate? YouTube is so trash because the comments just disappear. Do we make the constant rate being supplied an arbitrary variable k? Okay, it's not a variable, okay, it's a constant, right? But the dimensions of the dimensions of that constant is a rate, okay? So we just add it. I'll talk you through it by looking at the equation itself. The way in which we take into account that constant rate or that's being supplied to the reactor is by adding it, it's the lambda that I've added there. And you can see on top there I've said all three are rates. So the first one, dA by dt, is the rate of change of A with respect to t. Alpha A is the rate of decay, of A, and lambda rather is the constant rate that's being supplied into A. Okay, so lambda is not a variable. It's not a variable. It's constant, but the dimensions of that constant is of a rate. Okay, it's grams per second. Right, the rate at which it's coming in is at grams per second. The mass coming in is coming in at a rate of grams per second. And so it's not a variable, it's a constant that's being supplied to the reactor. My pasta's gone cold now. Okay, I want to quickly switch gears to chapter 3. A lot of you are not looking at my solutions. Matthew, I'll come back to chapter 2. Some of you are not looking at my annotated notes. So a lot of the questions that I received from students, I asked them if they'd looked at the annotated notes because a lot of the questions that they were asking me, I had answered in my annotated notes. So you've got to go to my annotated notes and see what I've said before asking a question. Before asking a question, please go back and see what I said. Okay. Chapter 3 now deals with a difference equation. So let's talk quickly what a difference equation is. A difference equation is an equation that models discrete or describes discrete change. And what we mean by that is the value of our function is dependent on different points or different intervals of that same function. So for example, if you want to know the way in which bacteria is growing, if you want to know what the current size of the bacteria population is, that growth rate is determined by the previous size of the bacteria population. Okay, so whatever the bacteria population was at hour 1 will help us determine what the bacteria population will be in hour 2, etc., etc. Okay, so it's discrete because we've discretized our independent variable time. Okay, so we're looking at what specifically what happens for discrete intervals, or in terms of a time, we're looking at for discrete points in time. Okay, so that's how the difference equation is. We're no longer differentiating, we're indexing. We're indexing across the independent variable. We're indexing across the independent variable. We talked about how to classify a difference equation. We classify it by its order. The order of a difference equation is the difference in the highest and the lowest interval, right? The highest interval and the lowest interval tells me the order of a difference equation. The next way we classified the difference equation was by linearity. And we said that each term in the difference equation must contain at most one term of the dependent variable. If there's more than one term of the, or more than one instance of the dependent variable, that difference equation is nonlinear. If the independent discrete variable occurs in a nonlinear way, that does not affect the linearity of a difference equation. The same thing with a differential equation. Homogeneity, the same thing applies, right? Under a transformation of the dependent variable does the equation remain invariant, and then lastly, what types of coefficients they were. We only considered one method for difference equations, and that was the ansatz method. So I'm going to spend a little bit of time with you now just to go over some of those aspects, because I think that some of you are misunderstanding or not getting the what I taught in the last lecture. When you talk about the ansatz method, we're talking about making an educated guess for the particular solution. A complementary solution follows the same method as we did for a differential equation. The structure is a little bit different. The way in which we formulate when there's repeated roots, when there's distinct roots, and when there's complex roots. Let me show it to you. I'll do an example of this. And that will replace the video that I was supposed to do. I wish I didn't. Okay, so to first find the complementary solution, we made this guess here, right? And using that guess, we found the characteristic equation, right? And then we said that we can solve this characteristic equation in three ways. The first is when we have distinct roots. And when we had distinct roots, this is what the complementary solution looked like. When we had repeated roots, this is what the difference equation looks like. In particular, I multiplied the second solution by a k to distinguish between these two because my roots were repeated. We did the same thing for a difference equation. The third is if I have complex conjugate roots. There are two ways in which to write this, either in its real form, right, which you need to understand how to unpack r and theta, or in its complex form. I've said that either is acceptable, but you need to know how to do both. You need to know how to do both, but either is acceptable. The next step was then to work out an ansatz. So let's do an example of that. And actually, let's do the example that I asked you to do. Right, so I said solve xk minus 1 equal to 2 to the power k. Okay, so let's do that question. Like I said, it's difficult to do questions on YouTube, but let's give it a go. So xk minus 1 is equal to 2 to the power k. So the first step is to find the complementary solution. Okay, we already found the complementary solution for the same question in the previous example. Okay, we found the complementary solution in the previous example. That's the same question. The complementary solution was equal to a constant. The complementary solution was equal to a constant. So, I'm not going to go over that again. What I want to do with you is the particular solution. So that was a constant. Now, how do I find my particular solution? How do I find my particular solution? Remember, to find my particular solution, I need to find an ansatz, and that ansatz is based on that function f of k, right? So f of k is equal to 2 to the power k, and I need to use this ansatz now, and use that function now to come up with my ansatz. So I'll take you back quickly to chapter 1. If I had in a differential equation f of x was equal to e to the 5x, if g of x was equal to e to the 5x, to work out my particular solution, remember that we said that this format here still needs to remain in my particular solution. And the reason why we said that is that the derivatives of e to the 5x still contain an e to the 5x. Okay, it still contains an e to the 5x, so my particular guess needs to be a e to the 5x. In a similar way, 2 to the k, in a similar way for 2 to the k. In a similar way for 2 to the k, my ansatz or my educated guess needs to include 2 to the k itself. Needs to include 2 to the k itself, right? And I'm going to multiply with a constant in front of 2 to the power k, sorry. 2 to the power k. Right, so that is the guess. I'm going to stop here just to, if you comment now on the video, if you don't understand this educated guess, then I can go through it with you again, right? Based on the function f of k, right, I make an educated guess for 2 to the power k as b2 to the power k. If you're unsure, please just message me now so I can go over that. Okay, now we've got to substitute this guess into my original equation, sorry, not that equation, but my original equation, this one on top here. Okay, so I can see that I need to substitute for x to the k, and I need to substitute for x to the k minus 1. So I know what x to the k is. I can now index across k to find what x to the k minus 1 is. So x to the k minus 1 is going to be b to the power 2k minus 1, which is going to be equal to a half b2 to the power k. Okay, you can check that for yourself that I've done that correctly. Okay, and now I can substitute a half b to the k and b to the 2k into my original equation there up top. So I'm going to get b2 to the power k minus a half b2 to the k is equal to 2 to the k. B multiplied by 2 to the k minus a half b multiplied by 2 to the k gives me a half b 2 to the k, and that's equal to 2 to the k. If I equate coefficients here, I get that a half b is equal to 1. Just want to check that that's correct. Okay, so in that instance, what we did was, it was 2 to the power k, and so I chose a guess of a constant multiplied by 2 to the power k. Okay, so that whatever is in the original equation is still, whatever is in my original equation is still in my guess. Okay, and I think if you don't understand the reasons for that, you need to go back to chapter 1 to understand how we made an educated guess. The reasons are the same. The reasons are the same. The reasons did not differ. Okay, so b over 2 is equal to 1, so b is equal to 2, and so my particular guess is, or my particular solution, remember my particular guess was b to the power 2k, so we've just found b to equal to 2, so my particular solution is equal to 2 multiplied by 2 to the power k. To ask what happens if you have a wrong guess, how do you make sure that you have the correct guess? Again, your question relates back to chapter 1. The way in which you know that your guess is wrong is when you get a contradiction. The way in which you'll know your guess is wrong is when you get a contradiction once you're trying to match coefficients. Under a correct guess, you will always be able to find a solution. And that is one way to know that your guess is correct. If you get something that doesn't make sense, go back and check your guess and adjust it accordingly. Go back and check your guess and adjust it accordingly. Okay, then the second example that I wanted to do with you involves, and I asked you to do both of them, so I hope that you've done it, x r plus 2 minus 4xr plus 1 plus 16xr equal to 4, 2 to the power r plus 26. Okay, so I'll post this later if I can, but I'm just going to talk you through this solution. Okay, so it's 4 2 to the power r plus 26. The first step is to find the complementary solution. So that's our equation there. The first step is to find the characteristic equation. So the characteristic equation there will be lambda squared minus 4 lambda plus 16 equal to 0, right? And that gives me non-real roots, and I can write out my complementary solution in that way. I can write out my complementary solution in that way. Now I've got to find a particular solution. Now I've got to find a particular solution. And the way in which I find the particular solution is to go to my function here, I will post the live stream once it's ended. I will post it to my YouTube page. Right. So now I've got to look at this f of k here, or f of r. If I look at this f of r, sorry, it should be f of r. What is to be? What is the guess for my particular solution going to be? So I have 4 multiplied by 2 to the r. So because there's a 2 to the r, 2 to the r needs to be explicit in my guess, and I'm going to multiply that by a constant. And remember, now I can have sums or products of good. Matthew's got the correct guess. It needs to be, I can have sums or differences or products of either of the cases that I accept. So here I have plus a constant, so I'm going to add a constant there. Okay, so that is what my particular guess should look like. Okay, once I have this particular guess, I can then index to find what x to the r plus would look like. Okay, so x, if that's my guess, x to the r plus 1, right? Wherever there's an r in this equation, I'm going to replace it with r plus 1. And x to the r plus 2, wherever there's an r in that equation, I'm going to replace it r plus 2. Okay, and once you do that, you can substitute into your original equation, and then you can match coefficients. Someone's asked, how long is this going to be? I'm going to end now. It's been an hour almost. That the way in which we find the educated guess for a difference equation for a particular solution is the same way as we found it for a difference equation, for a differential equation. Okay, look at the nature of the function and make your guess accordingly. But the key part here is to check for duplication again. If there's duplication between your particular guess and your complementary solution, you need to adjust your particular guess. You need to adjust your particular guess. And we did an example like that in class. We did an example like that in class where we needed to adjust the particular guess. Someone's asked me to do question 5 of TUT, or if you've got some other stuff to do, you obviously can do so. I will upload this to my channel in any case so that you can watch it. You can watch it again if you want to, or go back to it if you want to. So let's look at TUT 3 quickly and look at question 5. Okay, so let's just run through the questions quite quickly. Question 5, the particular guess is a quadratic there, so it's k squared. So my particular guess would just be bk squared plus ck plus d. Okay, we've run through questions like this. The interesting question here is question 6. Question 6 is actually an interesting question. You'll see, let's just look at the other questions quickly. I've done this one with you now. 12 multiplied by 4 to the k. Let's do that one. 12 multiplied by 4 to the k. So let me write out a question for you. So let's say, given f of k is equal to 12 multiplied by 4 to the k and the complementary solution was equal to a 4 to the k plus b to minus 1 to the k. And the question is, what is my particular guess equal to? What is my particular guess equal to? Given f of k is equal to 12 multiplied by 4 to the k, and my complementary solution, I worked it out to be this, what would my educated guess be? Well, some of you might be tempted. I'll give you a few seconds just to think about the 40 people that are left on the stream. I'll give you a few seconds just to think about what your particular guess should be, and you can comment, and I'll see if you're getting the correct answer. Okay, this is a good question. I hope that you're all trying it. Does anyone have an answer? Matthew, I see your response. I'll ask you to think about it again. Billions, I see your response. Okay, Matthew, you've got it right. Siferi Sithle, you've got it right too. All the way through, that's correct. Leah, I'll ask you to think about that, your answer. So those of you that got the correct answer, Billions, that's correct. Good. Edwin, that is correct. Good. Okay. Leah, that's correct. No, good. Awaheng, that's also correct. So it seems like you guys are understanding what's happened here. So some of you were tempted, like Sibongi Seni, to write an educated guess of a 4 to the k. Right? And some of you in the comments did do that, or rather, let's call it, because there's a in my complementary solution, let's call it c4 to the k. Tariq, that's good. Okay, c4 to the power k as an educated guess. You'd be tempted to beginning. Sorry, my legs are just dead now. But that would be incorrect. And the reason that would be incorrect is because we didn't account for duplication between my function, between my particular guess and my complementary solution. Because if I look at them as they stand, this term here and this term here are the same. Those terms are the same. And so to account for the duplication, I'm going to multiply my particular guess by a single degree of the discrete independent variable, and I get this to be my guess. Okay, so the aspect of adjusting your guess, does not go away. Okay, the aspect of adjusting your guess does not go away. So please do not make a mistake in the test. Make sure that you check for any duplications. Okay. Edwin's also, we shouldn't add a constant to the guess. No, we don't. We're not going to add a constant to the guess here because that is a power function. The general form of a power function does not include a constant. Okay, the general form of a power function does not include a constant. Same with the exponential function. So remember to write it out as in its most general form. Okay. Some of you in class, when we did the question, I chose the guess to be bk squared plus c, but I said we could have also chosen it to be bk squared plus ck plus d, which is actually the most correct answer because it's the most general form of a quadratic equation. However, adding the d does not matter because it would cancel out in any case. And it will cancel out because my general solution already has a constant in it. Remember, the general solution the general solution has to encapsulate the solution of the equation in its most general form, right? It needs to include all of the forms of the solution. So because our general solution already had a constant that came from the complementary solution, I don't need another constant. I don't need another constant. And so because of that, that constant's gonna drop off. So whether you add it or not, it's not gonna change anything, because the complementary solution already took into account that constant. Okay. Then I want to do question. I want to set up question 6 for you, and then I'm gonna think about it. So for linear and quadratic, you will add the constant, or just to be safe, if you've got something linear quadratic, add the constant just to be on the safe side, just so that you don't make an error, because that would be the most general form, right? So if you have f of k equal to k, your guess would be bk plus c, right? And if it was k squared, your guess would be bk squared plus ck plus d. Okay, so in its most general form. I want to do question 6 with you quickly. So it's x to the r plus 2 plus x to the r equal to 0. So someone asked if the particular solution is similar. Do we adjust by indexing? Yes. Adjust by the discrete variable. Yes. You would adjust by the discrete independent variable. Okay. Why are we not adding a constant in the power of the function? Because that's not the general form. Okay, that's not the general form. The general form of a power function is just a number raised to the exponent. Okay, it's just the number raised to the exponent. That's the general form, and so we just choose that to be the form. Okay, whatever the form is, if it's 5 to the k, that's the form. If it's 4 to the k, that's the form. Okay, that we don't change that form that's given in the equation. We do not change the given form. Okay, I'm going to do question 6, or I'm going to set up question 6 for you. Gideon asked me about question 6, and so maybe it's one that's worthwhile to do. So question 6 was x to the r plus 2 plus x to the r equal to 0. Okay, so if I find the characteristic equation, that's lambda squared plus 1 is equal to 0, which means lambda is equal to plus or minus I. Okay, if you write this out in the if you write out the solution in its complementary solution in its complex form, it would be a I to the k plus b into minus I to the k. But if I wanted to write out the solution in its real form, remember the real form said it should be r into sorry, is it r? A cos so I've just forgotten the form right now. Let me look at it again. Okay, so it should be r to the k a cos k theta plus bk sine theta. R to the k sorry, my mind's just not. A cos k theta plus bk sine theta. A cos k theta plus bk sine theta. Okay, and we know that r is equal to the square root of alpha squared plus beta squared, and theta is equal to arctan beta over alpha. Okay, so here to 0, beta is equal to 1. Okay, and so alpha squared plus beta squared is going to be 0 squared plus 1 squared. So it's going to be the square root of 1, which is equal to 1. Arctan, however, is going to be arctan 1 over 0. Okay, and then some students were emailing me to say, well, does the solution here, because we've got arctan 1 over 0, 1 over 0 is undefined. Does anyone know what the solution to arctan 1 over 0 is? So we had this differential equation. It looks very simple. Sorry, this difference equation. It looks very simple. It's a complex. It's just a complementary solution, right? It's linear second order homogeneous with constant coefficients. So we would think that it would be easy to solve. But to find the real solution, arctan 1 over 0. So what would the value of theta be here? Some of you are getting it. Two students are already getting it. Does it mean that there's not a solution? What does arctan 1 over 0 mean? It wants us to find out for which value of theta is arctan undefined. For which value of theta is arctan undefined? And you actually should have covered this in maths. What is the value of theta when arctan is undefined? And I'm going to leave that for you to do. So it does not mean that this question does not have a solution because of that undefined. That's not what it means. It's asking us to find the value of theta for which arctan is undefined. Some of you are getting it, which I'm very glad about, because it means that you're not compartmentalizing what you've done in maths. Okay, that's an hour and 2 minutes into the live stream. I know I didn't cover a lot. Is there any last minute burning questions? I can't please don't say do question 4 over that because it's going to take a long time. Is there any last minute conceptual questions that you want me to answer, or specific things regarding the test that you want me to answer before I stop the live stream? I can do so quickly. All right, so I'm going to give you a minute just to send through any questions that you may have for me, whether it's conceptual or specifics about the test or what it is that anything, right? Whatever you want me to cover, except for do a question, because I can't do a question. Okay, I think this YouTube thing is nice. It's just the comments are annoying. Okay, so Tariq asks, how will the readings be examined? Actually, there weren't any readings for this chapters. I don't think I posted any additional readings for chapter. Annie's asked a very good question. I can't repeat her question because it's going to give you the answer, but Annie, I like your question. Yeah, there weren't any specific readings. The main reading that I posted was the supplementary notes. It's not a reading, it's part of the notes. So the supplementary notes that I posted for chapter 2, which goes over the modeling process. Byron, I see your response. Good. The notes that I posted for chapter 2, those are examinable. Remember, there'll be MCQs, and it's within the MCQs that I will test concepts. While you're here on the live stream, the 47 people that are here, please attend tomorrow's or this week's and next week's lecture. It's vital because we're going to finish chapter 3 and then do chapter 4. So about Princess asked, would we have to derive the equations or just take them as it is? Some of you are probably studying the wrong way. No, Sudaksha asked, are we doing test 2 2018 tomorrow? No, we're not doing test 2 2018 tomorrow. We're doing new work tomorrow. We're carrying on with the work that we need to do. We're not doing revision tomorrow. Just got sidetracked there. What was I saying? I don't know. Yeah, it's vital that you attend the next few weeks, the next lectures, because they're important. I posted the test 2018 test 2. All of the questions in that test you won't be able to do. All of the questions in the test you won't be able to do because that test covers the direct method, which I haven't done with you, and it covers systems of difference equations, which is not in the test, and it covers more complex discrete models that we haven't done yet either. Okay, so please don't inundate me with queries. I will try and post tomorrow which questions you can do, but know that you can't do all of the questions in the 2018 test. Do not forget, please do not forget to go back to test 1 of 2018 and do the questions in test 1 of 2018 that wasn't covered in your test 1. So there's some nice questions in test 1 of 2018 on modeling, and the MCQs. There's some MCQs on modeling and some written modeling questions. Ishmael, when will you post the seating plan? I've already posted the seating plan. It's already up. I've already posted the seating plan. Please go and check it. Do you guys not get a notification when I post the seating plan, or are you guys just not checking your notifications? Which of the two is it? Because I posted that this afternoon already. The seating is up. When it comes to the modeling, because someone asked me, should we have to derive the equations again, or can we just use the equations? To not have an expectation that because we've done models of population and models of radioactive decay, that those are the models that that's going to be in the test. It's not what the case. That's not the case. Okay, that's not the case. What I mean by that is the questions that we've done is for you in order to think as a mathematical modeler, right? You need to be able to translate that thinking over. It's not that I'm going to learn how to do this question, and if a question comes out like this, I'm going to be able to do it. It's about the thought process. It's about the thought process. So please make sure you understand the modeling thought process, and not trying to replicate one of the models that we covered in chapter 2. So I'd rather you focus on thinking about the model than trying to memorize the model. Byron, I'm not going to respond to that. For the 2018 question paper, there's no solutions for question 3. Yes, I purposely took out the solutions for question 3 when I posted it at the time of test 1. What I'll do tomorrow is I will upload it with the memo. I'm hesitant to upload the memo very early. Maybe I'll only upload the memo on Wednesday, because I don't want you to look at the memo as I don't want you to use the memo as a crutch, or anytime you get stuck. I want you to struggle with it if you're not able to do it. And I'll post the memo probably on Wednesday only, so that you can attempt it first yourself and not have the memo to look at. Okay, so I will post the memo, but not today and not tomorrow. Any other final questions before I can go and finish my pasta, which is now cold? Any final questions? Matthew, I'll do so at some point. Any other question before I go? When computing the complementary solution for difference equations, do you want the real solution also? What do you mean? Do you want the real solution also? You mean if the complementary solution has complex roots? I'm assuming. So let me assume that that's what you're asking. If a complementary solution has complex roots, i.e., it's case 3, you can write it out as either in either its real form or its complex form. But you need to know how to do both. You need to know how to do both. Either is acceptable, but you need to know how to do both, which is different to chapter 1, because in chapter 1 I wanted the real form. I did not want the complex form. Okay, so here you need to know both. Guys, can you stop? My stomach's gonna pain because you're all discussing my pasta. Okay, so I think this YouTube worked out better than Instagram. I think the interface is much clearer. The only problem that I noticed is with the comments, and maybe it's because I'm not used to it, but the comments run through very quickly. So if it's unlike Insta, where I can scroll and I can see the comments, here they seem to disappear and I don't know where they go. So some of you, I did miss out your questions, because by the time I looked at it, it was already gone, and I don't see any. There's nothing on the page that allows me to change oh. So like I can see the questions now. We're learning. just see if there's anything that I forgot to answer. If our particular solution is similar, I've answered that. Okay, I think it's going to take a long time for me to scroll here. To do that. Okay. Billions, you said your question. I don't know where your question is, like, really. Suraksha's asked, will we have to draw graphs in the paper? Nice, that's a good question, and I'll not answer that question, but it's a good question. Will we be able to draw graphs? Or should we be able to draw graphs? That's a good question. In the differential equation, do we make the constant rate? Okay, so I've answered that. Ishmael asked, decaying substances always lose mass, but when it turns into another substance, how is that? We're directing the decay into another substance. Okay, that's what we mean. It's losing its mass, but we are directing that loss of mass to turn into another substance. Okay. Billions asked, can I do number 5 on TUT 3? I think that's simple. If you have any other questions that I haven't answered, and I know a lot of you have asked me questions on Instagram and on Twitter, if I didn't get to it, I apologize. But I will answer it in consult if you come and see me. There's a comment here that I do not understand. So Yuruna will upload the memo, and I will post this live stream to my channel. Okay. Yeah. So it's Annie said it's not going to be the same questions. That is true. Okay. I'm not going to ask you Model 3 in the test. It's not going to come out identically to it. It might be some version of Model 3, or it might be aspects of a model, but I'm not going to just replicate something from the notes, because you wouldn't have learned anything. Okay, you wouldn't have learned anything. Billion says, so does that mean I have to derive the formulas for decay and growth? That's the whole point of modeling. That is the whole point of modeling, is to start out with nothing and to come up with an equation. Okay? Start with nothing and come up with an equation. If I give you the equation in the test, I don't want you to learn the equations. Do not learn what the equation should be. Because I'm not going to give you the equation and the test and say, well, here's the equation, because that defeats the purpose. Right? There needs to be an element of model building that you do. Okay, so please, for the love of all that is good, please do not memorize equations. Please, students did this last year. Okay, last year in the test, students had memorized equations, and I'd asked a similar question, but I've changed it slightly, and students just regurgitated what they'd memorized. I can't believe that actually students have memorized what a solution was. Okay, so please do not do that, because that's not effective learning. That's not learning at all, actually. So please refrain from doing that. Right. Okay, we're 75 minutes into the live stream. It's gone on for too long. I'm talking for too long. This is like a double lecture now. That was not supposed to be the point. Will we be asked to graph the models we did in chapter 2? Like, again, you're asking me whether I'm going to ask you the same questions in the test. A better question is, should you be able to graph solutions? Yes, you should be able to graph solutions, right? And the questions like that in the TUT, sketch by inspection, what do you think this looks like? Okay, that's types of questions that you can expect. Okay, it was nice doing this. I hope that you learned something. I probably babbled on longer than I should have. But yeah, I'll see you guys in group 2, I'll see you guys tomorrow in class. Group 1, I'll see you guys on Wednesday. Please make sure to pre-read for class tomorrow. I will finish chapter 3 and I'll start chapter 4. So please make sure you attend the lecture. Please do not miss the lectures at this stage of the year, because if you do, you're going to be missing out a big chunk of the work. For any Jewish students who are observing a religious day this week or next week, all the best with that. And if you are going to miss my lecture, please make sure that you catch up accordingly. Okay, I'm gonna go now. Enjoy your night. Bye.